Welcome to the Deep Dive. Today we're digging into a paper that honestly feels pretty groundbreaking. It might just change how we think about training LLMs for, complex reasoning.
Oh, absolutely.
Imagine getting better results, sometimes way better results, by actually training on less data. Sounds almost too good to be true, right?
It does, but that seems to be what the Quinn team over at Alibaba and Tsinghua University have found.
Right. So, okay, let's do a quick rundown for everyone, that 1-minute version. What's the paper?
The paper is called Beyond the 80-20 Rule: High-Entropy Minority Tokens Drive Effective Reinforcement Learning for LLM Reasoning.
Okay.
And the core idea, the big discovery, is that when you use reinforcement learning with verifiable rewards, that's RLVR for these models, it turns out not all the words or tokens the model generates are equally important for learning.
Not even close, apparently.
Yeah, exactly. They found it's mostly driven by the small group of tokens that have high entropy. They call them forking tokens. Think of them as like critical decision points in the model's thinking process.
Okay, so forking tokens. And the practical takeaway. So what?
Well, the really surprising thing is, if you focus the RLVR training only on these high-entropy tokens, maybe just the top 20%, you can get similar or sometimes even better reasoning performance.
Better. By training on less.
Yeah, especially with the bigger models. It suggests a much more efficient way to train LLMs for reasoning.
Wow, okay, that definitely flips the script. So for all you AI researchers, ML engineers listening, this could mean a much smarter path to building more powerful models. All right, let's really unpack this. This sounds fascinating.
Let's do it.
So first, maybe just set the scene a bit. LLMs, obviously, they've gotten incredibly good at tasks that need complex reasoning, math problems, coding.
Yeah, they're powerful. And one of the key ways we boost that reasoning ability is using this technique, reinforcement learning with verifiable rewards, or RLVR.
Right. Can you give us a quick sense of what RLVR is, especially how it might differ from, say, RLHF?
Sure. So with RLVR, the model generates an answer, maybe a solution to a math problem. And then critically, we have an automatic way to check if it's right or wrong, a verifier.
Ah, okay. No human in the loop needed for the reward signal itself.
Exactly. If the answer's correct, the model gets a positive reward signal. If it's wrong, it gets penalized. It's optimizing directly for correctness based on something we can objectively verify, which is super scalable. It's less about style or safety like RLHF, more about pure reasoning accuracy.
Okay, that makes sense. So we know RLVR works, it gets results. But the mystery you mentioned was how it works deep down, like which bits of the model's output actually matter most for the learning.
That's the thing. Traditionally, we just apply the learning signal across all the tokens in the generated output. The assumption, maybe implicitly, was that they all contribute somehow.
Just treat the whole sequence as one big learning opportunity.
Right. And this paper really challenges that. They took what they call a pioneering exploration by looking at the reasoning process through this lens of token entropy patterns.
Okay, token entropy. That sounds technical. Can you break that down? What does entropy mean when we're talking about a language model generating text?
Yeah, it can sound a bit abstract, but think of it simply as a measure of uncertainty, or maybe choice, at each step of generation. When the model is about to produce the next token, how many different possibilities is it considering? How spread out are the probabilities?
So if the next word is almost certainly going to be, say, then the entropy is low.
Exactly, very low entropy. But if the model is at a point where it could plausibly go in several different directions, maybe introduce a new concept, make a logical jump, then the entropy for that next token will be high.
Like standing at a crossroads versus walking down a narrow path.
That's a great analogy. High entropy is the crossroads. Low entropy is the predictable path. Formally, it's calculated from the probability distribution the model assigns over its entire vocabulary for that specific token position.
Okay, got it. So they looked at these entropy patterns specifically in chain of thought reasoning, right? Where the model shows its work.
Yes, and this is where it gets really interesting. They found two key patterns. First, token entropy in Coding is absolutely not evenly spread out. It's heavily skewed.
Skewed how?
A huge majority of tokens have very, very low entropy, often close to zero. Like in their study, over half the tokens had entropy below 0.01. But then a small minority of tokens have high entropy. Only about 20% had entropy above a certain threshold they used.
So most of the generated text is highly predictable, almost automatic. But there are these specific points of high uncertainty, high choice.
Precisely. It's not a smooth landscape. It's mostly flat plains with a few sharp peaks.
Okay, that's pattern one. What was the second pattern?
Pattern 2 is about what these high and low entropy tokens actually represent. What kind of words are they?
Ah, the meaning behind the math.
Exactly. They looked at word clouds. The high entropy tokens, these are the ones they called the forking tokens, tended to be words that introduce choices or steer the reasoning. Words like if, assume, let, suppose, thus, however, wait, define. Logical connectors, words that kick off a new line of thought.
The crossroads words, like you said, they represent moments where the model really has to commit to a specific reasoning path.
That's the idea. And the low entropy tokens, they call them following tokens.
Okay.
These are the ones that just complete the structure. Things like word endings, punctuation, parts of code syntax, bits of mathematical formulas that are pretty much determined once you've chosen the path.
Just filling in the details along the chosen road.
Exactly. They're just carrying out the decision made at the last fork.
That distinction makes a lot of sense. So how did they actually test this idea that the high entropy forking tokens are the crucial decision points?
They did this really neat experiment using decoding temperature. Temperature, as you know, controls the randomness or exploration during generation. Higher temp means more exploration.
Right. It influences the sampling from the probability distribution.
Yeah. So what they did was selectively apply different temperatures to the high entropy tokens versus the low entropy ones.
Oh, interesting. What happened?
The results were pretty clear. Increasing the temperature, basically increasing the exploration or entropy, only for the high entropy forking tokens actually improved the model's reasoning performance.
So giving the model more freedom at those specific points helped it find better solutions.
Exactly. And conversely, if they decrease the temperature for those forking tokens, making them more deterministic, performance got worse.
And the low entropy tokens. What if you mess with their temperature?
Changing the temperature for the low entropy following tokens had very little effect on the final performance.
Wow.
And if you increase their temperature too much, making those predictable parts more random, the output could become nonsensical. It just broke the fluency.
Wow. Okay, that really isolates the importance of exploration, specifically those high entropy forks. You need the freedom there, but stability everywhere else.
Precisely. It confirms that these forking tokens really are the hinges upon which the reasoning turns.
Okay, so that tells us about the structure of reasoning itself. Now, how does RLVR training interact with this? Does the reinforcement learning process change these entropy patterns? Does it create new forks or smooth them out?
That's another really key part of the paper. They found that RLVR training actually preserves the model's underlying entropy patterns to a large extent.
It doesn't just flatten everything out.
No. The tokens that were high entropy before training tend to stay high entropy after. The overlap was really high, like over 86%, even after a lot of training.
Okay, so the basic structure remains. But what does RLVR change then?
What changes, and this is crucial, is primarily the entropy values of the tokens that were already high entropy. RLVR seems to fine-tune the uncertainty at those decision points.
Ah, so it's not building new roads, it's adjusting the signs or maybe widening the options at the existing crossroads.
That's a perfect way to put it. The low entropy tokens, the straightaways, they stay pretty much the same. RLVR focuses its adjustments on those critical forking tokens, likely optimizing how the model explores the different reasoning paths available at those points.
Okay, so it learns to make better choices at the choice points.
Essentially, yes. It refines the exploration strategy where exploration matters most.
Which brings us to the really counterintuitive part of this paper. Taking all these insights, they proposed a new way to actually do the RLVR training.
Right. This is the beyond the 80-20 idea. They thought, well, if the learning really happens at these high entropy forking tokens, what if we only apply the RL updates to those tokens?
So ignore the vast majority, the low entropy ones.
Exactly. They tried restricting the policy gradient updates to just the top 20% of tokens with the highest entropy in each generated response. They used a strong baseline algorithm called DAPO for this.
Just 20%? That feels drastic. What happened? Especially with their Quinn 3 models.
The results were frankly stunning. Discarding the bottom 80% of tokens from the update calculation didn't hurt performance. In many cases, it led to significant improvements.
Improvements. By doing less work.
Yes. On tough math reasoning benchmarks like AIM-24 and AIM-25, the gains were substantial. For their big Qwen 3 32B model, performance jumped by over 7 points on one benchmark and over 11 points on the other.
11 points. That's massive on a benchmark like AIM.
It really is. The 14B model also saw solid gains, around 5 points. Even the smaller 8B model held its own or improved slightly.
That's incredible. So focusing the learning signal on just that critical 20% actually unlocked better reasoning performance, especially in the bigger models.
It appears so. And to really drive the point home, they did the opposite experiment too.
What, training only on the low entropy ones?
Exactly. Training exclusively on the bottom 80% lowest entropy tokens. And the result, performance tanked. It got much, much worse.
Okay, that really seals it. The value is concentrated in that high entropy minority. The rest might even be noise for the RL process.
That seems to be the strong implication. Low entropy tokens don't contribute much to the reasoning improvements and might even hinder learning if you force updates on them.
And you mentioned this effect was stronger for larger models.
Yes, they showed a clear scaling trend. The performance benefit of focusing on the top 20% forking tokens became more pronounced as the model size increased from 8B to 14B to 32B.
That's a super important finding for anyone working on, frontier models. Efficiency and better performance.
Absolutely. It suggests this isn't just a quirk, but potentially a fundamental aspect of how these large models learn complex reasoning.
So why? What's the hypothesis for why focusing on just that 20% works so well? Why isn't 10% better or 50%?
Their explanation centers on the idea of exploration. Those top 20% high-entropy tokens seem to hit a sweet spot for enabling the model to effectively explore different reasoning pathways during RLVR. If you focus on too few tokens, say just the top 10%, you might be restricting exploration too much, not giving the model enough levers to pull. If you include too many, like 50% or 100%, you start applying updates to those low-entropy deterministic tokens.
Right, which we saw can be useless or even harmful. You introduce noise where you need stability.
Exactly. It seems like you're potentially diluting the learning signal or forcing the model to explore in parts of the generation where it really shouldn't. So that 20% threshold appears to optimize the balance between targeted exploration at decision points and maintaining stability elsewhere.
It's like teaching a student. You focus on the concepts they struggle with, the decision points, not on drilling things they already know automatically.
That's a very good analogy. RLVR, optimized this way, becomes a much more targeted teacher.
This is fascinating. And the implications go beyond just making RLVR more efficient, right? You mentioned something about generalization.
Yes, this is potentially a really big insight. The paper suggests this focus on high-entropy tokens might help explain why reinforcement learning often leads to better generalization than supervised fine-tuning, or SFT.
How so?
Well, SFT typically pushes the model towards generating one specific correct answer, often reducing entropy across the board as it learns to replicate the training data. This can lead to overfitting or memorization.
It learns the answers, but not necessarily the underlying reasoning process.
Exactly. Whereas RLVR, especially when focused on these forking tokens, seems to preserve or even slightly increase the entropy at those decision points. It maintains the model's flexibility of reasoning paths.
Keeping the options open at the crossroads.
Right, which is crucial if you want the model to handle new, unseen problems that require adapting its reasoning. They even tested this on an out-of-distribution dataset, Life Code Bench, and found the forking token-focused RL still outperformed standard RLVR.
Wow. So it suggests a mechanism for why RL helps models think more flexibly, not just memorize.
It definitely points in that direction. It also highlights a difference between LLM reasoning and maybe more traditional RL tasks.
Oh, how are they different in this context?
In many classic RL environments, maybe like a game, every action choice might be equally uncertain or important. But LLMs generating language, especially CoT, have this built-in structure from pre-training. They need low entropy segments for fluency and coherence.
Right. Language isn't just a series of independent, equally weighted choices.
No. And that's why some standard RL techniques, like adding a general entropy bonus to encourage exploration everywhere, might actually be counterproductive for LLMs. It could mess up the low entropy parts.
Because it doesn't respect this natural split between forking and following tokens.
Precisely. Techniques like the clip higher mechanism in DAPO, which selectively boosts exploration for important steps, align much better with this finding because they implicitly target these high-impact, high-entropy moments.
This really reframes how we should think about applying RL to language. So, looking ahead, where does this research go next? Is there more potential here?
The authors suggest there is. They showed that even with their improved method, just allowing the model to generate longer responses, extending the context length from 20K to nearly 30K tokens, pushed their scores even higher on AIM-24 for the 32B model.
So, simply giving the model more room to think allowed this optimized process to find even better solutions.
It seems so. It hints that we might not have hit the ceiling yet, even with this focused training. Maybe combining it with other techniques or different data could unlock more.
Are there any caveats or limitations we should keep in mind?
Definitely. The authors point out a few. First, the really strong results were primarily on their Quinn models. They tried it on Llama 3.18b, and the results weren't as clear-cut without doing some supervised fine-tuning first, suggesting there might be interactions with model architecture or pre-training.
Okay, so maybe not universally plug and play just yet.
Potentially. Also, the experiments focused heavily on mathematical reasoning. How well this holds up in other domains like, say, complex programming, creative writing, or really abstract reasoning tasks is still an open question.
Right, different tasks might have different entropy dynamics.
Exactly. And that specific 20% figure they found optimal, that might not be a magic number for every single task or every RL algorithm. It could need tuning.
Makes sense. Standard research caveats apply.
Always. But the core insight seems really robust.
Absolutely. So let's just wrap this up. This deep dive has shown us something pretty fundamental. Effective reasoning in LLMs, especially when boosted by RL, seems to hinge on a surprisingly small set of high-entropy forking tokens.
Yeah, it's not about brute forcing learning across the entire output. It's about intelligently focusing on the critical decision points where the model needs guidance to explore and refine its reasoning pathways.
And for everyone listening who's building or studying these models, this gives us a new lens, right? A way to potentially train models much more efficiently and maybe even achieve better generalization by understanding where the learning really counts.
It's a powerful reminder that digging into the mechanics down to the token level can unlock significant progress. Efficiency and performance often come from understanding how these things work, not just that they work.
Definitely. Which leaves us with a final thought to chew on. If optimizing just 20% of tokens during RL can lead to these kinds of leaps in reasoning and maybe generalization, what other hidden drivers or similar 80-20 rules might be lurking within LLMs?
That's a great question.
Could we apply this kind of forking token thinking to other areas, like unsupervised pre-training, or maybe even understanding how multimodal models integrate different kinds of information? Where else are the critical choice points that determine success?
Lots to think about there. It opens up many new avenues for investigation.
It certainly does. Something for all of us to ponder until the next deep dive. Thanks so much for unpacking that paper with us.
My pleasure. It was a fascinating one.